Astronomers just detected methanol, life's most critical building block, pouring from interstellar Comet 3A/ATLAS at levels that defy explanation. This visitor from another star is releasing prebiotic molecules in concentrations far beyond anything seen in our solar system. What star system creates chemistry this extreme? And if the raw ingredients for life flood through interstellar space at these levels, are we underestimating how common they really are? Let's dive right in. When astronomers first locked onto 3I/ATLAS, something felt immediately wrong. Its trajectory revealed a hyperbolic orbit. This object wasn't trapped by our sun's gravity. It was just passing through. But that wasn't the part that got scientists talking late into the night. The comet started releasing gas far earlier than it should have. We're talking about outgassing beginning at distances where solar system comets remain frozen, solid, dormant, and inactive. It was as if 3I/ATLAS had been sleeping for hundreds of millions of years, and the slightest warmth from our sun triggered a cascade of chemical activity that defied every model we had. What had this traveler experienced during its unimaginable journey through the cosmic void? The Atacama Large Millimeter Array in Chile, one of the most powerful radio telescope networks humanity has ever built, turned its full attention to this interstellar wanderer. When the spectroscopy results came back, the team didn't trust them. They ran the analysis again and again. The data didn't change. Two dominant chemical signatures emerged, hydrogen cyanide clinging close to the nucleus, exactly where it should be, and methanol absolutely flooding the surrounding gas cloud in concentrations that made no sense. The methanol levels weren't just high, they were impossibly high by every standard we'd established from studying comets born in our own neighborhood. We're seeing concentrations that exceed our local comets by factors that frankly challenge what we thought we understood about how comets form and evolve. Now, when scientists call methanol life's most critical building block, they're not being dramatic. Methanol isn't alive. It's simply CH3OH, one carbon atom bonded to 4 hydrogen and 1 oxygen. Basic organic chemistry. But here's why it matters profoundly. Methanol acts as the gateway molecule in chemical evolution. In laboratory experiments and astrophysical models spanning decades of research, methanol consistently appears as the bridge between simple volatiles and complex organic compounds. It's the starting point for formaldehyde, formic acid, and eventually the amino acids that form proteins, the machinery of all life we know. When you detect methanol at these extreme levels, you're not just finding one interesting molecule. You're finding hard evidence that the chemical pathways leading toward biological precursors are active and efficient. Does this prove life exists elsewhere? Absolutely not. But it demonstrates that the fundamental chemistry enabling life isn't some rare cosmic accident unique to Earth's neighborhood. It might be common. It might be everywhere. The ALMA data revealed something even stranger that nobody anticipated. Scientists expected methanol to sublimate directly from the comet's frozen nucleus, just like hydrogen cyanide was doing. That's standard behavior for cometary ices. They heat up, turn to gas, and stream away from the nucleus in predictable patterns. Clean physics, well understood. But methanol wasn't following the script at all. Instead of concentrating near the nucleus where it should originate, methanol was distributed broadly throughout the entire coma, the vast cloud of gas and dust surrounding the comet's core. The hydrogen cyanide behaved normally, sticking close to its source. The methanol spread everywhere, as if it was being generated across a wide area rather than just sublimating from frozen deposits. This distribution pattern suggests something remarkable is happening. Either methanol exists frozen throughout multiple layers of the comet's internal structure, embedded in countless dust grains that fragment and release their cargo as they drift away from the nucleus, or something even more fascinating is occurring. Methanol is being actively produced through chemical reactions triggered as sunlight interacts with the coma material. If that second possibility is real, we're not just observing a comet releasing stored chemicals from its formation billions of years ago. We're watching new chemistry emerge in real time, processes that our solar system comets simply don't display. Earlier observations caught another critical detail that ties everything together. When telescopes measured the sunlight reflecting off 3I/ATLAS, they detected a distinctly redder color compared to typical comets from our region. That reddish tint isn't just aesthetics, it's chemical evidence written in wavelengths of light. Red coloration in deep space objects usually signals organic compounds that have been processed by radiation over immense timescales, or surface chemistry that formed under fundamentally different conditions than what we see locally. Combined with the methanol data, that red hue paints a picture of an object chemically transformed by its environment. Was 3I/ATLAS born in a region of its home star system so cold and carbon-rich that methanol production dominated the chemistry? Did it form in zones where temperatures and radiation allowed molecular reactions we simply don't see in our solar system's comet-forming regions? Or did hundreds of millions of years, drifting through interstellar space, bombarded constantly by cosmic rays and radiation, fundamentally alter what this comet was when it first left its birthplace? The scientific community is carefully considering each possibility, and the implications stretch far beyond this single object. If 3I/ATLAS formed in a carbon-rich, volatile-loaded region of its parent star system, those environmental conditions would naturally favor efficient methanol production on icy grain surfaces. Our solar system doesn't have zones quite like this in the regions where comets form, but there's no cosmic law requiring other star systems to match our architecture. This comet could be delivering a direct sample from a fundamentally different type of planetary environment, one where organic chemistry followed pathways we've only theorized about. Some researchers propose that the comet's interior might contain significant amounts of iron-bearing minerals intimately mixed with water ice. When heated, these metallic compounds can catalyze reactions producing methanol as a byproduct. This scenario is particularly intriguing because it implies a formation history where metals and ices combined in ways rarely seen in our comets. If planetary systems form with different starting materials or under different gravitational and thermal conditions, their comets would naturally reflect that diversity. Then there's the possibility that simply existing in interstellar space for millions or billions of years fundamentally changes an object. Cosmic rays, high-energy particles streaming through the galaxy, slowly bombard and alter surface chemistry. These processed outer layers might respond to solar heating differently than pristine ices, releasing certain molecules more readily or breaking down into new compounds through radiation-driven reactions. This could explain both why 3I/ATLAS began outgassing unusually early and why its methanol appears distributed so widely. The comet may have been chemically weathered by its long journey in ways we've never had the chance to observe before. The reality is probably more complex than any single explanation, and that complexity is actually more revealing than a simple answer because it tells us that the universe generates chemical diversity through multiple pathways operating simultaneously across billions of years and countless environments. Let's be clear about what this discovery means for the search for life beyond Earth, because this is where careful science becomes genuinely profound. Methanol doesn't prove aliens exist. It doesn't mean life arose in 3I/ATLAS's home system. What it does prove is that the chemical infrastructure for biological complexity exists in environments we've never directly sampled before. Every distant star system we study through telescopes is separated from us by light years. We can analyze their light, but we can't touch their materials or measure their chemistry up close. Until now. This comet traveled from one of those unreachable systems and delivered its molecular cargo directly into our detection range. The fact that it carries methanol in such extraordinary abundance means that wherever it originated, the chemical pathways that could eventually lead toward biological precursors were not just present but actively efficient. Carbon chemistry wasn't a rare accident. It was productive enough to saturate an entire comet's composition. Now scale that insight across the galaxy. If one random interstellar visitor arrives methanol-rich, how many others are traveling through space with similar or even more complex chemistry? How many of the trillion star systems in our galaxy are generating organic-rich materials in their planet-forming zones? We've studied thousands of comets from our local neighborhood and built comprehensive models of solar system chemistry from those observations. But 3I/ATLAS is already showing us that what we consider normal might actually be just one variant in a vast spectrum of possibilities. Our neighborhood might not be representative at all. That's the question 3I/ATLAS forces us to confront honestly. What if chemical diversity across planetary systems is so extreme that our carefully constructed understanding of comet composition only applies locally? What if the building blocks of life are being manufactured in environments scattered throughout the galaxy at scales we've dramatically underestimated? Every day, 3I/ATLAS moves farther from Earth, and our window to study this extraordinary object narrows. We're racing to capture every possible measurement, tracking how its chemical profile evolves as it heats up, watching its activity patterns change, searching for additional compounds we haven't yet detected. But we're limited to remote observation, watching from millions of kilometers away. We can't send a spacecraft. By the time we could design, build, and launch a mission, this visitor would be long gone, continuing its endless journey through the galaxy. The opportunity to physically sample material from another star's planetary formation zone is slipping through our fingers. Some scientists are seriously proposing standby missions, probes built and ready to launch on short notice when the next interstellar object appears. The cost would be staggering. The technical challenges, immense. But we'd gain something no telescope can provide, actual physical samples from environments we can never reach, analyzed in laboratories with precision impossible from a distance. We'd hold in our hands material that formed around another star billions of years ago. That's not just science. That's answering questions humanity has asked since we first looked up at the night sky and wondered what else is out there. So, what does 3I/ATLAS really tell us? This comet traveled hundreds of millions of years from another star system and delivered proof that methanol, the gateway molecule to biological chemistry, exists at extreme concentrations in environments beyond our solar system. This isn't speculation. It's measured data from one of the most powerful telescopes on Earth. We've now studied 2 interstellar objects in detail. Both have shown chemistry that doesn't match our models. Both have challenged what we thought was normal for comets. If the first 2 visitors are this different, what will the next 100 show us? The evidence is mounting. The chemical building blocks of life aren't rare cosmic accidents. They might be everywhere, manufactured across countless star systems in ways we're only beginning to understand. And every interstellar visitor that passes through our solar system brings us one step closer to answering the biggest question we've ever asked. Are we alone? If this discovery changed how you see the universe, smash that like button right now. Subscribe to Galactic Breaking News and hit the notification bell so you never miss the space stories that matter. Drop a comment below. Do you think organic chemistry is common across the galaxy? Let's discuss. More cosmic mysteries are coming. See you in the next one.